Hello, science class. Today we're going to be talking about tropical Alberta. So this is chapter 2 in our geology unit, and we're going to be focusing on kind of things that have happened after that has led us up to getting so much oil, and then how do we find oil and gas in Alberta. So our title is Tropical Alberta because, well, we had to have all this plant life, we had to have an explosion of life, and then we had to trap it all to get this oil and gas that we have now. Hopefully we follow through on these notes or this recording, and then we're also going through on our geology workbooks. I can't stress this enough, these geology workbooks, there's links on D12 or we had the paper copies, but there is lots and lots of vocabulary to review, and that's going to be the big thing here, is reviewing and understanding a lot of this new vocabulary that we're going to be coming up against through this chapter. So as we go through it, I'm going to recap briefly fossilization, but I'm going to go quicker through the notes just so it's not as long of a video, and I'll explain some of the key details. But with the notes, I'm not going to be reading through it because hopefully we can read through at our own pace. I just want to go through and kind of highlight the following processes, something like this, about how do we fossilize. And the basics are life, death, burial, preservation, discovery, and recovery. And hopefully we understand through this life and death, but then we have these bones buried. However, when we preserve them and fossilize them, it's not the actual bones that are left, but rather an impression, or we're having a cast of what the bones and the space they actually took up. So the bones will get covered by rock, but over hundreds of millions of years, the bones will actually dissolve, and then water will seep in and leave other minerals, and it will actually turn what the bone was, and it'll fill it with a mineralized rock of sorts. And it'll be a different rock than the surrounding rock, leaving a cast or an impression rock. And then we have to discover it, and then we recover these fossils. So I'm going to talk about some of those key details like that, but for the other notes, you're going to have to make sure you're reviewing terms like a mold, okay, and how we have these external molds and internal molds, but I won't be reading through a lot of these details because you can go through the notes and the copies on D2L yourself. What we see here are just kind of cool images that we would have seen for fossilization, and we would have seen these different things fossilized. And under the perfect circumstances, they can leave really cool impressions, and we get a good idea of what were some of the creatures of past times. So here I'm walking through some of the details a little bit more kind of written out, and we want to make sure when we see or come across these terms that we're double checking them with our course outline book, and we are filling in our notes for fossilization. And so we're coming across these terms such as petrified or pre-mineralization. And when we had these soft-bodied organisms, why do we think it's hard to actually preserve soft-body organisms like ourselves or a fish? Well, it's very quickly eroded. Things like our soft tissue, or those are the things that are usually eaten, so they're not really left behind. It's only the hard bones or the things that don't get eaten that are usually preserved. Or that's why we see a lot of those trilobites or things with shells, because just a lot of organisms don't eat the shells, so they're left to be covered and they decompose very slowly, where soft tissues goes very fast. And so these ones, they cannot be fossilized by this replacement where we have this slow process because it's just usually not left behind. And it's a rare case where we have fossils that have given insights into feathers or skin. And that's where the now dinosaurs were believed, or some dinosaurs were believed to have feathers because now they found fossil evidence of, oh, they might have actually had some feathers on some. So when we review, here is a mold, or sometimes what happens is there's these impressions, and then they can form a cast from these soft body impressions. Make sure you're always going back and understanding some of these fossils. I showed this image earlier when we started talking about geologic time, but make sure we're going back to it and you can kind of see some of the fossils and these index fossils to relatively date in generalized periods or generalized forms. Like you'll see those Cambrian explosion trilobites, they won't really necessarily be paired up with some of the fish that we see in later life. So I talked about this Cambrian explosion again off of that trilobites and having all this basic material. So if we remember when we talked about, okay, here's life and it exploded. Well, generally, we can find all the basic life forms or the basic body designs for animals can be found way, way back when, about 545 to 250, 225 million years ago. So this 20 million time span is actually very, very short when you're talking about 4.6 billion years. And so it's a very short time frame to see this amount of life explode, making it a very important time. And so we could trace back all modern groups of animals back to this Cambrian period, and what we're going to see is you'll have to go to this link, but I provide links in the video so you can actually click on these YouTube videos and help supplement. So when you go to the notes, you should have the link to actually click on. Now, here we're going to see all kind of crazy organisms that we just don't know what they are, and they look completely foreign and alien. However, we share the basic body structures, not saying we're here with bugs or reptiles, and arthropods or reptiles were very, very different, but like I said, the basic body structures were developed, even though they looked much, much different than today. This Cambrian explosion brings us to one of the most important and probably the biggest discoveries in the world, and it's right in our backyard, and this is called the Burgess Shale. And so again, if you need to, there is a link posted with the Burgess Shale, and that'll take you to where Burgess Shale is. But actually, like I said, it's right in our backyard. If we head towards the mountains and go just past the Alberta border into BC, you will see in Yoho National Park this massive, massive, massive preservation of Cambrian fossils, and it's so wonderful that it is a actual World Heritage Site and it's preserved by UNESCO. And so why this is so important? Because 500 million years ago, the Burgess Shale was underwater and it was very shallow near the equator, meaning where Alberta roughly was, it was very tropical and full of life. This is going to become very, very important. Here we're going to see some images of what the Burgess Shale actually looks like today. And you can see it's just the side of a mountain, but based off of what we know with some basic rock knowledge is when we look at these rocks right here and we see all this layering, we see this very, very fine, fine sand where we classified it as a shale. So it's very, very fine, but it breaks off in these very fine layers, revealing great preserved specimens and just the amount of organisms and the amount of clarity from this site helped jump ahead fossil records and all this dating so much. And here you can see again the layering, and some of these layers are just found on the ground just like that, and you could pick up rocks just like this and you could find fossils in these rocks. That's the issue too, though, is it needed to be a World Heritage Site, because if you just have people coming in and taking their fossils, there wouldn't be much left to discover. So this is what an example of what it would have looked like as a shallow coast that 500 million years ago, with all this life just waiting to be discovered now. So what exactly happened? How did we get this perfect situation where we could discover all this life? Well, unfortunately, we have to have these perfect conditions for extinction, because for us to find fossilization, usually we see some kind of catastrophe. That starts up with an underwater avalanche. And so what happened was there was an avalanche that traps all this sea life under a thick layer of mud. And this mud is great for preserving, but not so great for having all this life survive. So it would have been a very large extinction of life because we had this very large mudslide that happened underwater covering all this life. And so, because there is this mud layer and it trapped it very quickly, there is very little oxygen for any decomposition. And so, yes, they would have died, but they wouldn't have decomposed, leaving a lot of any potential soft tissues to actually be preserved and filled in as a cast. And then we would have had fossilization and actually created these wonderful fossils that we see today. So this muddy grave, unfortunately, it was the perfect situation for all of these fossils because, well, they all collected in the shallow water, just like how life right now collects and lives in these shallow waters. You can think of all these nice coral reefs. It is full of life. Well, tropical Alberta was much the same. It was warm, shallow waters, and it also contained some deep water organisms because it was just the perfect situation of full of life. All these animals are found, and in this soft mud, it would have been a wonderful reef side to view back then. And for us, we can sort of view it because we did have this kind of underwater avalanche or this underwater mudslide. Here we see an image of what it would have looked like before, and the seafloor was there. It had shallow life, and then it had this deep water life, but something happened. This reef top all of a sudden gave way, trapping everything under, and you can still see how you have this big mudslide of everything trap everyone underwater and gets trapped. 500 million years ago, the landmass that kind of is BC comes crashing in and it pushes it up to become a mountain. And we see this now in Yoho National Park, where it's a mountain of fossils. So we see here a collection again of the Burgess Shale, and we see what the side of the mountain looks like. But then we also see a collection and some of the drawings of early scientific work back in the 70s when they started to discover all these organisms and drawings and how perfect and how kind of cool they actually looked. So let's recap real quick. All these animals are underwater. They got trapped by underwater mudslides. They had low oxygen levels, but it was still present in the atmosphere. Animals were preserved. They were fossilized. This mountain was pushed up real quick, and then this erosion occurred over hundreds of millions of years, and we see these fossil layers kind of preserved for us to actually find. And then if you go west of Banff, so Banff is on the Alberta side, if you kept going past Banff into BC, into Yoho National Park, you will see this Burgess Shale collection. And so now we can have it dated back to the Cambrian period, making it very, very important. Okay, now that we're getting into dollar values and not just $1 million reef, but $1 billion reef. Well, how do you ask? Well, I'm going to go quicker through it now because I'm going to go through a catalog of different periods and getting younger and younger as we go. And so this $1 billion reef is in reference to oil and this oil and gas because that's what Alberta is stock full of. Okay. So as we go up through our geologic timescale, if you pull one out, you're going to see the Ordovician period, and this is where fish started to evolve, and we start to see them pop up. And at this point, Alberta was still underwater, still allowing us to have these huge reef systems, allowing us to have all this life still. Now, in the Silurian and Devonian periods, Alberta was still underwater, which is great because, well, it's just collecting all this massive amount of carbon. And all this life was living, dying, getting covered up, and adding a lot to our current future. And so now these aquatic life plants started. Okay, we've talked about a lot so far, and we've updated our notes in our workbook with them. And make sure to practice these terms. I didn't include these questions in the workbook, but please pause the video here right now, take some time, or pull them up in your textbook and see if you can actually answer these questions with some detail, whether it's a thought question or if you actually want to write them out or go back and review the process. Please be sure we're reviewing these questions.